A customer visits a retail website, clicks 3 items, adds a pair of shoes to their cart, and stops. Will they actually click the buy button or simply close the tab? Sarah, a data analyst at North Star Retail, has 8,000 recorded customer sessions just like this sitting in a standard spreadsheet. Her goal is to build a model that predicts what a shopper will do next. This scatter plot shows her initial approach. Traditional machine learning attempts to partition these shoppers by drawing a single, definitive mathematical dividing line through the data. It groups the likely buyers on one side and the casual window shoppers on the other. The reality is that human behavior is inconsistent. A customer might browse for an hour and buy nothing, or log on and spend $300 in 2 minutes. Human decisions rarely fall neatly on either side of a perfect geometric boundary. When you try to map complicated behavior with a straight mathematical edge, the model fails to capture the nuance. For decades, the basic building block of artificial intelligence was a unit called a perceptron. It is a single mathematical neuron that takes in inputs and makes a binary choice. A single perceptron computes a basic equation and outputs a single threshold. It operates exactly like the rigid boundary Sarah started with, slicing information into 2 flat halves. This graph shows what happens when information is structured as an exclusive or XOR problem. The data points are arranged in a distinct checkerboard pattern. No matter how you angle or shift a single straight line on this grid, you cannot successfully separate the categories. Feed it 1,000,000 rows, run it on a supercomputer. The structural limitation remains. To accurately trace the overlapping, complicated reality of how people act, the mathematical logic must have the capacity to bend and curve. Predicting nonlinear outcomes requires moving beyond these linear tools. This diagram illustrates the first architectural fix, stacking. By wiring multiple individual perceptrons together, we create an input column that feeds into a hidden middle layer, which finally funnels down to a single output. This is a multi-layer perceptron. But stacking these nodes alone is insufficient. In mathematics, combining multiple straight lines together still results in a straight line. We have to inject a specific mathematical rule between the layers, called an activation function. As data passes through the network, this rule alters the flow and introduces nonlinearity. Because of this specific adjustment, the logic can now curve, fold, and twist itself to fit the tangled checkerboard patterns that linear models cannot handle. Connecting layers of nodes and adding a nonlinear rule turns a rigid calculator into a flexible engine capable of contouring to complex data. Having the capacity to learn is only the first step. The training happens in a fraction of a second when this network makes a mistake. The cycle begins with a guess. The network ingests a specific customer's data through its layers and predicts an outcome. This chart compares that initial guess against the actual outcome. The system calculates the precise difference between the two, which is defined as the loss. Now, the system walks backward through its own architecture. This step, backpropagation, traces the error from the output back through the hidden layers to pinpoint exactly which connections contributed most to the incorrect guess. With the source of the error identified, the network alters its internal weights. It nudges its connection strengths slightly closer to the correct answer. The size of that nudge is governed by the learning rate. Move too aggressively, and the model overshoots the answer. Move too slowly, and the system fails to arrive at the solution within a reasonable time frame. Deep learning is an automated, relentless loop. Guessing, measuring the error, tracing the source, and making an adjustment. After hundreds of iterations, Sarah checks her results. On her specific dataset, the complex neural network performs with similar accuracy to the classic linear models. But judging this architecture by its performance on a small spreadsheet misses the broader implication. This exact same multi-layer structure and 5-step learning loop can be scaled up to process radically different, massive datasets. Replace basic spreadsheet rows with image pixels, and the network creates computer vision. Replace those with billions of text tokens, creating large language models. The neural network is the engine driving modern artificial intelligence. It is a single, adaptable equation, continuously taking tiny mathematical steps toward the truth.